Hi everybody, it's Mrs. Peachy from Physical Science, and I'm going to be doing the second half of your roller coaster portfolio tutorial right now for you guys to look at in order to figure out how to do the math associated with this portfolio. Last portfolio, we kind of give you some instructions on how to build your model roller coaster. And now you just need to do some calculations. So you're going to be calculating potential and kinetic energy at different points throughout the track. Now remember that the track that I made is different from the one that was in the instructions in that it's just quite a bit smaller. So when you are doing these calculations, you're going to have to take that into consideration, okay? So the numbers, if you make a different track than what is presented to you in the sheet that goes with this, your numbers will be different. Okay, very warm in here today. All right, so start off by you do need to know the mass of the ball that you use. In this case, we used a marble, if you remember correctly. I wanted to kind of give you kind of some idea of what different things, the masses of different objects. So a large paper clip, which about like this size, the bigger paper clips, these are about 2 grams, okay? And so you can kind of think to yourself about how many paper clips does my marble weigh? So I would say the marble that I have weighs about the same as 10 paper clips, so about 20 grams is the mass that I'm going to be giving the marble that I had, 20 grams, okay? Now remember, when we're looking at these units of measure, we don't want grams. We're actually looking to have it in kilograms. So there's 1,000 grams in a kilogram. So I need to take that 20 and divide it by 1,000. 20 divided by 1,000 should be tired. 20 divided by 1,000, hang on a sec, would be 0.02 or 2/100ths of a kilogram, okay? So that is going to be the mass, and I'm going to put that somewhere here just so I can keep track of it. Okay, so maybe I'll put it under question number 1 for now. My marble was 0.02 kilograms. Okay, but then the question is on there too, does your tennis ball, or in this case marble, make it to the end of the track? Why or why not? The numbers that we do keep the same are the 9.81 meters per second squared, because that is the acceleration due to gravity no matter what. But the other ones you're going to have to kind of measure. So you're going to need the height of your hill at various points along the track. Remember that potential energy is mass times gravity times height. Mass times gravity times height. So for potential energy, I'm always going to be calculating mgh. For kinetic energy, it's 1/2 mass times the velocity squared, but I don't know that. I don't know what the velocity of the marble is. So do not use the 1/2 mv squared for kinetic energy. Instead, you're going to calculate total energy and then subtract potential energy from that. So total energy minus potential energy is equal to kinetic energy. So there's some assumptions that we're making here, and that is that the energy is maintained at all points throughout the track, which is a false statement because we do know that there's friction along the track and that the ball is slowing down as it moves along the track. However, we are going to make the assumption that this is a frictionless track, even though it is not. So when we're doing our calculations, we're going to base it on a frictionless track, not one that has friction, okay? So the very first point at the top of your first hill is going to indicate how much total energy there is. This is going to be the highest height. So you cannot have any more total potential energy than that which is stored at the top of the highest height, okay? So anywhere else along the track, you will not have any more energy than this. This is my total energy. So I got to measure the height to the top of the very first hill. You're going to want to use the centimeter side of your ruler, okay? And remember that we're going to convert this to meters at the end, okay? So I'm getting a measurement of 20 centimeters. And centimeters, there are 100 centimeters in a meter, right? So 20 centimeters, well, 20 divided by 100 is 0.2, right? So there's the top of my highest hill is 0.2 meters. Move my face here a second. So I have, what did I say, 0.02 kilograms times, so MGH, 9.81 meters per second squared. Oh, just a moment. Hit the wrong button there. Where did it go? Just a moment. I seem to have lost my worksheet. Just a second. Okay, I found it. Too many tabs open at one time, that'll happen to you guys. So, all right, so that's your acceleration due to gravity, and then the height was 0.2 meters. So we needed to calculate that equals. So on the calculator, I'm going to take the 9.81 meters per second squared times 0.02 kilograms times 0.2 meters, and that gives me 0.04. And that's kilogram meters squared. Oh, this should, meter squared per second squared. So that should have been a square here. That's where I went wrong before. That's where I ended up entering something that switched my tab somehow. I must have hit a tab button. So that would be Newton meters, or AKA joules, right? So that's the top for me, 0.04 joules. That means that's the maximum, okay? So it's always going to be 0.04 joules here. So when you are calculating, you're only calculating potential energy. Okay? And remember that kinetic energy is just going to be that 0.04 minus the kinetic is equal to the potential. So in this case, I have my potential is the same, so I'm going to say 0 here because it's not in motion at the top of the hill, right? So wherever you calculate the potential energy, you will calculate these using MGH, okay? These you get from subtracting the potential energy from the total, okay? So the 0.04 joules that I have as total energy, that's what I got because these are my numbers. Your numbers might vary, so that means you might get a different total energy. I do want to see this, though. I want to see this calculation, so please put that up on your question here. It says, describe the relationship between potential and kinetic energy. So let's try to think about that for a moment, shall we? Up at the top here where the ball is not in motion, it's all potential and no kinetic. Once the ball starts to move, what happens to the total potential energy? Okay, what happens to the total kinetic energy? When it reaches the bottom of the first hill, it keeps going. So now, as it's going higher and higher, it's starting to slow down, right? So less velocity means lower kinetic, but more potential, because it's getting higher. As it goes back down, potential energy is decreasing, because the height is decreasing, but its velocity is getting greater, so it's increasing its kinetic energy. So you notice that as one increases, the other decreases. So they're always inverse. They're always equal, well, not necessarily equal and opposite, but they're always opposite of each other, right? And they always total the total energy in the system. Okay? And again, we're going to ignore friction, even though it's definitely in there for sure. Okay? This is the question. Was friction negligible? That means can we really ignore it? I mean, we have been ignoring it, but is that truly what we're seeing? Yes or no, and why? Okay? So that is all the math that you need to do for this portfolio. If you have additional questions, feel free to give me a call at extension 2204 or send me a webmail message. Have a great day, everybody.